Well, welcome everyone. Welcome to those of you who were with us here last night and all the newcomers as well. And I've been told that we're on social media tonight, so those of you, and I know that we have a number of students here, if you want to tweet about whatever is going on, and whatever that means, you do hashtag Trottier. And you can tweet away or make any other bird sound that you want. You know, ever since humans found themselves on this earth, they looked up at the sky and wondered what is up there. And looked up there hopefully, thinking that maybe one day we may be able to defy the Earth's gravity and start our trek into outer space. Most of which, of course, was science fiction until just a few decades ago. But we also wondered not only about whether or not we would be able to go out there, but whether or not we would be visited by others from outer space. So we've wondered both of these directions. But as I was saying, it only started to become a reality relatively recently. In fact, it was Robert Goddard, the American physicist, who really began the age of rocketry, launching what really was a pretty primitive rocket. It was a first liquid-fueled rocket. He launched it in his Aunt Emma's cabbage patch, and it flew only for a few seconds, but within a relatively short time, he was launching bigger rockets, not very successfully, you can see. But by the 1930s, he was launching relatively large rockets. And then the war came along, and so did German technology. And the Germans launched the V-2, which really was the world's first spaceship. It traveled a lateral distance of several hundred kilometers, and it reached the upper atmosphere, almost getting into space. That was designed by Wernher von Braun, who was an engineer. And at the end of the Second World War, when Hitler ordered that his rocket engineers should be killed, lest they be captured, he gravitated to the American side and became the head of the US space program, eventually designing everything from the very simple Redstone rockets to the giant Saturn V that eventually made it to the moon. And the space race was on. In the 1950s, that was a heyday for science. There was a lot of money available for research, for everything to do that could be connected to space. But the US was stunned by this headline when the Russians managed to accomplish the first real big deal, which was putting Sputnik into orbit around the Earth. It really didn't do very much. It had a transmitter inside that would transmit a beep every time it passed over Washington. And that was irritating enough. It became even more concerning when the Soviets put a man inside a larger Sputnik, and that, of course, was Yuri Gagarin, who made it into Earth orbit, demonstrating that they had the capability of achieving a speed of 17,500 miles per hour, which is what it takes to overcome the pull of gravity. And the Americans were not able to do this at that time. In fact, the first American space flight was not an orbital flight. It was a single-man mission, Alan Shepard, and it was a suborbital flight. It was to be only about 15 minutes. And this was a very big deal in the US. It was widely advertised. The television networks were watching. And because it was only designed to be 15 minutes, there was something that hadn't been thought of. Because there was a hold in the countdown, there was a problem that needed to be fixed. And the hold kept getting longer and longer and longer. And astronaut Shepard was inside of the capsule, ready to be launched. And then nature called. And this was a problem because no provision had been made for this, since it was to be a 15-minute suborbital flight. And the hold kept getting longer and longer and longer, and he didn't know what to do. He switched to an emergency channel, and he informed the control room that Something had to be done, otherwise there was going to be more than one launch. And there was panic in the control room, and they didn't know what to do. But eventually the engineers decided that even though he was covered with telemetry equipment, they would allow him to urinate into his spacesuit, which is exactly what he did. And there is Alan Shepard, ready to be launched, lying in a pool of urine. And this is one of those little secrets that the world is unaware of. The mission was a successful one, and of course, eventually it was followed by a number of other successful missions, including, of course, Apollo 11, the landing on the moon, and Neil Armstrong, and his classic remark, of course, one small step for man, one giant leap for mankind. He probably should have said humankind, but he did say mankind. And not only did they land on the moon, but of course they successfully returned from the moon, launching the lunar lander with an Earthrise in the background, and coming back to Earth, landing, plunking down in the ocean. That's a fact. We've been there. We've been to the moon. What's next? Well, there's new technology on the horizon for the possibility of penetrating deeper into space. The next step, logically, would be Mars, and we already last night heard a little bit about that, saw the Mars rover and what it is capable of doing. But much, much further out are other stars with other planets revolving around them, the exoplanets, which you will hear about in a few minutes from our first guest. But even those exoplanets are basically in our neighborhood, and our galaxy, the Milky Way, is one relatively insignificant galaxy in a universe of billions of planets and stars, and inconceivable virtually the size of this. But we have made that one small step. And that step, that footprint, is going to stay on the moon forever, because of course there's no wind on moon, so our footprint is there. And Robert Goddard started it all. And he said that the dream of yesterday is the reality, is the hope of today and the reality of tomorrow. And we have achieved some of his realities. We're going to hear about some more today about what is possible, what we can look forward to in terms of the exoplanets. And we're also going to hear a little bit about what isn't quite as real. Because there are a lot of myths associated with space travel as well. Like last night, we are going to hear from two speakers. Our first speaker is Professor Sarah Sager, who comes to us from MIT in the US, but she was born in Canada, in Toronto, and is a proud Canadian. And we, of course, are very proud of her because of all of her achievements. Her PhD was from Harvard. She was a MacArthur Fellow, which I can tell you is a very, very big deal. A couple of years ago, she was recognized by Time magazine as one of the 25 most influential women in space exploration. And she has been called the Indiana Jones of astronomy. And I think that when we listen to Sarah, we will know exactly why she has been given that label. Her discussion will be followed by Joe Nickell, the Sherlock Holmes of solving mysteries. He is a unique man, perhaps the only one in the world whose career and life right now is dedicated to solving some of the world's greatest mysteries. And he has solved mysteries about Jack the Ripper's diary, which turned out to be a fake. He's an expert in analysis of inks. He's an expert in looking into mysteries such as Bigfoot and alien abductions, and I suspect that you will hear some of that. So we've got sort of interesting combo here, Indiana Jones, Sherlock Holmes, but we're not going to be talking fiction. We're going to be talking real science. We're going to be talking evidence. So I'd like to turn the podium over to Professor Sager, who's going to inform us and entertain us as well about stories of exoplanets. If you want to use the remote.
Good evening, everyone. Thanks for coming out to my talk. I'm excited to tell you tonight about exoplanets and the search for planets like Earth. We call it the search for Earth 2.0. Here's a real photograph of a dark sky. The camera that took this picture is much more sensitive than our eyes, but I hope that you've all been able to go to a dark sky. How many of you have seen the stars, like in this image? Well, next time you go out to a dark sky, when you look up, you can actually know that astronomers have found, statistically speaking, that each star you can see in the sky should have at least one planet. And indeed, I want to start out by reminding everyone that every star in the sky is a sun. And if our sun has planets, we should naturally expect that all of those other stars should have planets also, and they do. So many planets out there. There must be billions and billions of planets in our galaxy alone. And we think our universe has upward of hundreds of billions of galaxies. So just the number of stars out there is literally mind-boggling. I usually tell the audience, well, you can do the math, but it's actually, none of us can really even fathom in our heads just how many stars and planets are out there. So what we aim to do eventually is to find another Earth. And this actually is a real photograph of our Earth, as seen from the Voyager 1 spacecraft from 4 billion miles away. Now our Earth itself, an Earth around a nearby star, would not be fainter than, would be about as faint, I keep having to correct this, but it would be about as faint as the faintest galaxies ever observed by the Hubble Space Telescope. So Earths are faint, it's within our reach. But the problem is that Earth is right next to, any Earth would be next to a very bright star. Like our Earth and Sun, our Sun is 10 billion times brighter than our Earth. So we have to have a way to find a planet next to a very bright star. And for the short term, that is really hard to do. And so I won't be talking about that problem today unless I get asked about it in the Q&A. But right now, what we're going to do is I'm going to explain to you a shortcut, how we're going to choose the easiest planet finding technique and the most favorable kind of star. And it's like a shortcut to Earth 2.0. So I'll get to all of that, but here's what I will talk about today. And these are the questions I get asked most often, and they're by children and students and colleagues, other scientists, just people of all walks of life, actually. What is an exoplanet? When and how will we find another Earth? The question actually I get asked most often is, can we go there? Can we travel to another one of these Earths if we find one around a nearby star? And if we can't go there, why are we looking? And in fact, I got asked this question today when I spoke to an undergraduate class of McGill physics students. So to start out with, what I'm going to do is tell you a little bit about exoplanets that we know about right now. And I'm actually going to use this program that I hope all of you will download later. It's from NASA. It's called Eyes on Exoplanets. And here it's showing you an image of what we think our galaxy would look like. And it's showing you in that little circle, most exoplanets have been discovered within 1,000 light years of our sun. So let me try to see if I can go to it. I've downloaded the program already and I'm connected to the internet. And so one thing you can do is you can take a view from Earth, and this is a real map of stars all around us. And basically what they're showing here is stars in the sky, and these ones that are highlighted are ones that have known exoplanets around them. So you can go here and you can click on some of these stars and see what's going on. But this tool actually allows you to zoom out. I really genuinely love this tool. I'm not involved in creating it or trying to sell it in any way. But you can go out and see how things look from far away. There would be our moon's orbit. Now it's showing you can see Earth, and further away to see all of the stars. Imagine if we're zooming out past our own Earth, and eventually it'll show us all the stars all around us. So what I'm going to do is take you on a tour of my, let's say, 2 or 3 favorite planetary systems. And then anyone in the audience, if you have a favorite, you could start thinking about that now. You can actually, I'd like you to sort of suggest that in a moment. And if you don't, I have a bunch of my other ones. So let me start out by one of my favorite ones. And it is called Kepler, from the Kepler Space Telescope, Kepler 11. So let's see, it can combine it here, Kepler 11. So what this program will do, it'll take us to Kepler 11. It's a sun-like star. Its distance from Earth is about 2,000 light years. There it is. We wouldn't expect you to recognize it in the star, but look, it's showing you a view of the planets around Kepler 11. There are 6 planets that are known. And just for a second, there's this cute little thing here, how long to travel to that star. So it starts out by automobile at 60 miles per hour, 22 billion years. If you could figure out how to travel at light speed, that'd be a little different, but it's still 2,000 light years. Far. Stars are far apart. Stars are far away. But what actually is so interesting about this planetary system is you see how it looks a bit reminiscent of the solar system. It's got a bunch of planets and orbits about its star. But what you can do here is compare with our solar system. Now look at that. Look where Mercury is. And Venus. Oh, this is showing Earth. Oh, this is Mercury's orbit here. What it's essentially showing you, Venus is quite hard to see, it's right here. Look at this, all of these planets here, 1, 2, 3, 4, 5 planets, all orbiting its star at the equivalent of what would be interior to Mercury's orbit. And when these were found, would you think that all of these planets are little rocks like Mercury, small, tiny, rocky planets? That's what I would have thought, because when we observe stars forming, we don't see enough material close to the star to form lots of bigger planets. But in fact, some of these planets are bigger than Earth, and some are of low enough density, but that we believe they must have a significant hydrogen component. So with this system, what I'm trying to say is we don't really know how this system came to be. We think the planets must have formed further from the star where there's more material, and somehow all migrated inwards, interacted with each other and with the disk and other planets, and got kind of knocked inwards. There are many, many systems like this, actually, many what we call compact multiple object systems. Okay, now I'm going to show you one. I have one other one to show, and then I may ask you to suggest one. You're going to probably wonder if I know every single planet by name. Okay, here. So the reason I like this one, HG 189733, by the way, I wish we could all have a planet named after us, but in this case, it's a catalog name. Henry Draper, a long time ago, cataloged all the bright nearby stars, like the sun. And this is one of the early exoplanets that was discovered. And why I like this one is it's our most favored planet for atmosphere follow-up. We study atmospheres of a handful of favorable planets. And this one is arguably the best studied. It's a giant planet. It's very close to its star. It's bright enough and near enough to Earth that we get enough photons so we can study it in detail. Let's compare with our solar system. Whoa, look at Mercury, and there's the planet. Now this is a giant planet. Let's see, I don't know if it says here anything about it, but it's in a 3.5-day orbit. It's so close to the star, 10 times closer to its star than Mercury is to our sun. And this planet is heated by the star to about 1500 Kelvin. It's super hot on this planet. So, you know, if we were to go through this, let's go through this exercise. Does anyone want to just call out one of your favorite planets? Okay, one right there. Yes? Planets. Or if you can name a star if it has a planet around it. Pardon me? Let's see. Well, there is a star that's called Virginis. I could look at that one for you. There is Virgo itself is a constellation, so you'd have to be specific about which star in the constellation. So actually, you know what? I'm actually going to show you one other one. Just I'm showing you the variety of exoplanets here, and I think you might be... Instead, I'm just going to show you this other one for a moment, HD 80606. This one is really interesting. I mean, they're all interesting. It's like all your children are your favorites. All the planets are great. HD 806, wow, look at that. This particular one, compared with our solar system, the planet, see this very elliptical orbit? Incredibly elliptical. It's almost like a comet. This thing is really, I'll zoom out a little so you can see it. It's got a 100-day period orbit, yet it's so elliptical. And so what I'm trying to get at here for you is for you to get a glimpse of the diversity of exoplanets. They come in pretty much all masses, all sizes, all distances from their star, all orbits, anything imaginable, that I like to say that in exoplanets, anything is possible within the laws of physics and chemistry. Now, the flip side to all these planetary systems we have found is that we have not found a copy of our solar system. So out of all those stars out there, when before exoplanets were discovered, we just thought there'd be so many copies of our solar system. In fact, we haven't found one yet. Now, our solar system turns out to be very hard to find because the techniques we use to find planets, they favor big planets and planets that are close to the star. And ours is quite hard to find, but we could safely say that something like less than 10%, around 10% or less of sun-like stars could have a solar system like ours. So 1 in 10 or even 1 in 20. We're actually saving questions for later, so hold on to that question. So now I'm going to get back to my talk. I hope you'll look at that software a little later and tell you a few other introductory things about exoplanets. Here's an artist's conception of exoplanets, but I just want you to know we have no idea what exoplanets look like. In a sense, we basically only measure their size or their mass, or sometimes we get their orbit. We don't have any pictures of exoplanets like this. This is artist conceptions based on theory and modeling. But the one thing we do know, so the one thing we do have that we're looking for that we can find right now, is a planet in the so-called habitable zone or Goldilocks zone. This is an artist conception showing you a sun and these kind of color-coded regions where we're looking for a planet that's the right temperature to host life. And that would be a planet that's not too hot, not too cold, but just right for life. And here it says that on the bottom, and also not too big, not too small, just right. And here it's showing you conveniently a planet that looks like Earth, just right. They're showing you one that's too hot. Molecules, complex molecules won't be able to form in a very hot environment. And in a too cold, water would be frozen out. We think water is required for all life on Earth, and so our search actually is going to focus on planets that could have liquid water. So to the first part of my talk, to answer what is an exoplanet, it's a planet that orbits a star other than the sun. Thousands of exoplanets are known to exist, and we expect, based on statistical observations, that nearly every star has a planetary system. So that's your background. Hopefully we're all on the same page now. And now I can move on to how and when will we find another Earth. And to introduce this topic, I'm going to start with this photograph, again, a real photograph. And this was taken about a decade ago. I was actually consulting for National Geographic. So I'm sure many of you read the magazine, and it has such a high standard. The writers are incredible. The fact checkers are unbelievable. And same with the photographers. And our analogy about trying to find an Earth twin is it is as hard as trying to see a firefly in the glare of a searchlight, when that firefly and searchlight are thousands of kilometers away. Very hard to do. Well, they wanted to take the picture of how hard it is to do that. So National Geographic, they rented the searchlights, put it in a field, and tried to make this photograph. But remember what I told you before, that our Earth is 10 billion times fainter than our sun. And so in a camera, I'm sure you can imagine, actually, especially here in Montreal, because it's such a snowy city, you know how you try to take a picture in the snow, and everything's either all whited out, or it's all dark? Because the contrast, you can't actually take a picture that can see really faint things and really bright things all together. So it's the same here. They couldn't actually take the picture. But the first thing I complained about was, see the searchlights on the left, how there's 4 of them all stuck together? Because stars don't behave that way. We don't have stars that are all stuck together in a cluster like that. That was the first comment. The second one, if you look at that firefly, I think you can tell, I hope actually, it looks fake. It's faked. They couldn't actually take the real picture, but they put the fake one there anyway, just so they could have the picture. But the point that really astonished me was at first the photographers came back super excited. They were like, wow, we couldn't take the picture of the firefly beside the searchlight, but we could actually take a picture of the firefly in front of the searchlight, blocking out light from the searchlight. And so what they did was they actually discovered a planet finding technique that we already knew about. And that is, while we can't find the Earth in reflected light yet, we actually can see Earths when they go in front of their star and block out a tiny bit of light. And that's what I'm going to be talking to you about the shortcut, and how we're going to find Earth 2.0 in the not too distant future. And so to give you numbers, if we want to use so-called direct imaging, where we look for the planet directly and block out the starlight, that's 1 part in 10 billion problem. That would be like asking yourselves to make a measurement to 10 decimal places. Anything is so hard to do at that level. And actually, I sometimes ask the audience, have any of you ever had to make a measurement to 10 decimal places? You know, sometimes someone puts their hand up. You know, it's physicists who work on gravity when they're trying to test like Einstein's and stuff like that. So usually no one has even conceived of measuring something like that. It's very hard to do. Now, if we want to transit, an Earth-sized planet going in front of a sun-like star, that signals about 1 part in 10,000. But I'm guessing that for many of you, many of us, all of us, probably haven't made a measurement to that level either, to 4 decimal places. And you know what? Finding a big Earth transiting a small star, that's a part in 1,000, which sounds a lot easier compared to a part in 10 billion. And so that's part of the shortcut. So to describe what a transiting planet is, here is a graphic. It's an artist's sketch. You can see an image of a sun-like star on the top. We don't see any stars like that other than our sun. Instead, we can measure the brightness of a star as a function of time and hours, and this animation will show you an Earth-sized planet in front of a sun-sized star. Do you see the planet? And now look at the graph, though. What happens? You actually see a tiny drop in brightness when the planet goes in front of the star. And would you believe that that is the currently favored planet-finding technique? We actually have, like, literally hundreds of thousands of people hours have gone into this, and the Kepler Space Telescope has literally revolutionized astronomy, bringing big data to exoplanet science and to astronomy. And with these transits, this is showing you just a few out of thousands of transiting planets known. Look how they're all different. We would call this like a family portrait of some planets, depending on where in the star the planet is crossing, how big the planet is compared to the star, and a bunch of other factors. The light curve, we call it, the transit light curve, actually looks very, very different. And here, this figure I actually pulled off of Wikipedia, and what it's showing you is a function of time. It's showing you a bar chart. So it goes from 1988 on the left until, it was actually from September 23rd, 2014. And it's showing you different methods of planet binding techniques. So I'm not going to explain all the different ways to find planets. It's just that green bar is transiting planets, planets found with the transiting technique. You can see blue is another popular technique, radial velocity, and every technique has its heyday. Right now, we're just sort of living in the time of transiting planets. And so the transiting planet technique is how we're going to search for Earth 2.0, and we have one other trick, and that is to look around the most favorable star. You know, there are so many star types out there. The yellow one represents our sun at 1 solar mass. It's, again, an artist's conception. For comparison, on the right, it's showing you there are some blue-white supergiant stars, 150 solar masses, and much bigger than the sun. At the bottom, you're seeing, to scale, part of a red giant star, very old stars that have evolved from stars of some stars like our sun. And then on the left, you see a small star, a red dwarf star, at 0.08 solar masses, the lower limit. Now, do you see the little black dot that I've put on to represent an Earth-sized planet? Does it look bigger to you around do you think that's like the same size planet, or do you think I put like a bigger one around the small star? I mean, the thing is, it looks bigger to me around the small star, actually, but in fact, it's exactly the same size. And I think it goes to show you that if we look for a transiting planet around a small star instead of a sun-sized star, it's actually just easier to see. And so actually, that is our, let's see. Okay, so that's what we're going to do. So I have to add one more thing about these planets around the small stars, and that is the so-called habitable zone or Goldilocks zone. In the middle, you see sun-like star. It has a habitable zone. At the bottom, you see the smaller star has a habitable zone closer to the star, because smaller stars give off less energy, and small rocky planets are heated by the star. And so what this means is that the habitable zone is closer to the star, and this makes the techniques favorable for many different ways. But I know that there are some astronomers in the audience and some astronomy students and some sort of people who are a little more in the know. And I wanted to tell you that this so-called Goldilocks zone or habitable zone is the reason for a lot of fighting going on right now in astronomy. And just sort of thinking of what level to tell it to you at, but what we imagine is that this habitable zone could be quite wide, and that is because of the greenhouse effects on planets. Here on Earth, we're concerned with our climate warming, and we're worried about carbon dioxide at the parts per million level being added to our atmosphere. Imagine for a moment if our planet had double the amount of carbon dioxide, or 100 times more, or if we were on a bigger planet than Earth that had a very massive atmosphere that had lots of greenhouse gases. Our planet would be so warm. And what this means is that planets very far from the star could actually be the right temperature for life. Some people have even proposed that rogue planets ejected from their planetary system could actually be right. And there's like a vigorous debate going on right now. So although we're not totally sure where the boundaries are, we still hold this concept of the atmosphere is warming, keeping the planet warm, but that the energy comes from the star itself. So what I want to do next is to hit the concept home of this so-called Earth 2.0, is take you on a virtual trip to one of these habitable worlds. This is an artist's conception of a planet that would be in the habitable zone of a red star. And they've made the sky red and purple, just that's the artist's license there. But what we think would happen if we could actually take a trip to such a planet was the star, the sun, would be very big in the sky. And the artist has also shown some other planets in the system. One's transiting, one looks like a moon, but it's supposed to be another planet. And what I like most about this planet, if we could go there, is it's so close to the star that it actually gets to what we call tidally locked. It shows the same face to the star at all times, just like the moon does to Earth. It's just a favorable energy end state. And you know what that means if we were on this planet? It means that the star, or the sun, would be in the same place in the sky at all times. So if we went there, we could go where the sun is always setting. Or we could go, I don't know where you would go. Would you go to where it's always daytime? Or the astronomers would want to go where it's always nighttime. And on this planet also, because it's closer to the star, by Kepler's laws, it has a shorter year. It goes around the star For sort of a favorable case, it would take maybe 20 days to go around the star. And what that would mean is that for any children in the audience, your birthday would be every 20 days. That would be a problem for the parents, though, right? Because having a birthday party every 20 days would be intense. But what that means for astronomers is often in astronomy, for whatever reason, big discoveries are made just before the sun moves into position, and it's daytime when your object is in the sky. So for astronomers, that cycle would go much more quickly, and you'd be able to observe things more often. But one thing I want you to know is that going to a planet like this or living on one might not be such a great idea after all, because these M stars, they're very active. They give off flares, and these flares could be very disruptive to electronics. Forget about using your iPhone and playing video games. It may be very harmful to life because DNA and other things are really quite fragile to high energy particles. Maybe life has to live on the dark side, or maybe subsurface, I don't know. So these worlds are quite different from our own, but they just happen to be the easiest ones to find right now. So the shortcut to Earth 2.0, a super Earth, or we call that a big Earth, translating a small star. So to answer this part of the talk, how will we find another Earth? We will use transits, the most favorable planet finding technique. We will search small stars with habitable zones close to the star. And we'll consider super Earths, that is planets bigger than Earth, but that are known to be predominantly rocky. And I'm going to add a few notes about how we're going to do this. MIT has we have a space telescope mission called the Transiting Exoplanet Survey Satellite. It's an MIT-led NASA mission to launch in 2017. It's an all-sky survey. TESS builds upon pioneering telescopes such as the Canadian MOST Space Telescope, the Corot Space Telescope from France and ESA, and especially the Kepler Space Telescope. The ultimate goal is to find the closest 1,000 M stars with transiting planets and a source list for the James Webb. I'll come back to that in a minute. And by the way, that cartoon at the bottom, that's Kepler 11, the very first planetary system that I showed you. It's just a cartoon version of it. So what it is you can see the four, this is just a artist's drawing of it, but there's four essentially very specialized telephoto lenses. They have giant baffles on them, and each one has a 24 by 24 degree field of view. It's based on a past heritage of precision photometry. Here's a real photograph too. This is, you can see on the left, there's George Ricker, he's the PI. There's myself. On the right, another physics professor, Josh Wynn, and the deputy PI, Roland Vanderspecht. This is a mock-up of the model to show you it's not all that big, actually. The whole spacecraft, it would be like a very big industrial type of like washing machine. And you can see the antenna for communicating back to Earth. Here's a picture of the lens. We had to actually, a full prototype camera had to be built, two actually, and successfully demonstrated before the mission was selected by NASA to go forward. We actually put the smallest guy with the lens to make it look as big as possible. And on the outside at the top, there's a baffle that's there to block out light, ultimately, from the moon and other objects. And that baffle actually was made with a 3D printer. It's not what's going to be used to make it for space, but just to get it going. And these prototype lenses were tested. They were shaken to demonstrate that they could withstand the vibrations of launch. And they were also thermally cycled to show that nothing would break or explode as the spacecraft would orbit Earth and heat up a bit and cool down. Essentially, it has a 100 millimeter effective pupil diameter, and just for the people who like optics, it will go from 600 to 1,000 nanometers, a broad band to get all the photons that it can collect to do this study. And here, there's a video here, so if you want to later on Google TESS YouTube exoplanet, you'll come to a video, and it shows you a unique orbit among other things. And what I've done here is just captured a part of how it's going to observe the whole sky. In 4 years, it will have these sectors. Each of them is for one camera, 24 by 24 square degrees. And the cameras, it was hard to tell, but they're made so that they get a strip, a 90-degree long strip in the sky made of 4 sections. And it'll look at that section for 26 days and then move on, eventually tiling the whole sky. But I think the part that might be of interest to you, that how would you handle observations of millions of stars? Well, if we look at millions of stars just to find some planets, we imagine a kind of funnel technique where we have hundreds of thousands of stars, and thousands of them show the transits, like the little light curve with the drop in brightness of interest, where we would actually want to find planets. But we have to do a variety of traditional now exoplanet conventional follow-up techniques. But imagine having hundreds of thousands of stars and funneling to 2,000, then 500, then 100, just to get to like 50 prime candidates of big Earths transiting small stars that actually might be in the habitable zone. It will actually involve people around the whole world using ground-based telescopes to help follow up on the signals that we find. So how and when will we find Earth 2.0? NASA MIT test launch 2017. It's an all-sky survey for super-Earths transiting small stars. If an Earth exists, we have the capability to find and identify it by the 2020s, and I'll come back to that in a moment here. But what people really want to know is, if we find these Earths, if we use TESS and many ground-based telescopes, and on my visit here, I learned that René Doyon at the University de Montreal has a great new instrument called Spiru, and it's going to go in Hawaii on the Canada-France-Hawaii telescope, and it'll help out with TESS by making some measurements of the light curves of the stars that look like they have planets around them, and he'll also do his own survey. So the whole world who can contribute to this will, and so we'll find stuff if it's there. So when we find this planet, these group of planets, what will we do? Everyone always wants to know, can we go there? And so I do feel compelled to address it. And to do that, let's talk about distances. This projected sun, this is a projection of a real photograph of our sun. Now let's think about Earth for a moment. And how big do you think Earth would be compared to this image of the sun? The dot, yeah, there's a clue. That's actually a sunspot. I had to search for all the real images of our sun to find just the perfect one that had a sunspot. That's about a little bigger than Earth would be, but that's basically how big Earth would be compared to the sun. But the next question is, if this is the size of our sun, where do you think Earth would be with respect to this image here? If that's the size of Earth, that's the size of the sun, where is it? Do you want to raise your hand if you think it's where you are, or we have someone at the back of the room? Anyone else? I guess maybe you're either shy or thinking about it. You know, there's a little trick here, just it's total coincidence, but it turns out that the Earth is about 100 sun diameters away from the sun. So think for a moment, if you could stack like 100 of these beside each other, it wouldn't be at the back of the room. But thanks for putting that in, because you were the farthest person away, so that was a good try. Where do you think this would be, actually? You have to name a street. There's a street probably a few blocks away. But think about that for a moment. It's pretty far. Did you want to say something? 5 kilometers? I don't think it would be quite that far. I'm guessing that image is about, let's see, okay. Yeah, probably not quite as far, but let me think about it for a second. So actually, Earth is quite far away. Someone said many blocks away, but now if we were to pause for a moment and think about where would the next star be? If this is the size of our sun, the next star actually would be further away than Vancouver from here. So planets are far from stars, and stars are very, very far from each other, actually. Space is vast. It's so huge. And when we want to think about, can we go there, our nearest star, Alpha Centauri, is 4.22 light years away. Our Voyager 1 spacecraft, it's actually going so fast. It's traveling at about 20 kilometers a second, zipping by. Actually, it would take over 70,000 years to reach the nearest star. And that would be if it was headed in the right direction. So this is actually a problem. How can we go to another star with another planet? But you know what? The question I get asked most often is because the interest is so huge. There is an organization called the 100-Year Starship, which was started by DARPA. It's a branch in the American government. And they now run, hoping that 100 years from now, we will find a way to do this. There are serious individuals out there, including higher-ups at NASA, who believe there are techniques where we could travel at some fraction of the speed of light, maybe a tenth, maybe half the speed of light eventually. And so I really believe someday we're going to find out how to do that. But one thing is that, imagine for a moment that we could travel at the speed of light. Let's say we found a way to do that and go on a spacecraft. It would take us about 40 years to reach the nearest star. And I didn't count speeding up and slowing down or anything. But when you think about like what age would be a good age to do that, actually it would be a good age, I actually think, if you're in your early 20s, because at that age, you still have those 40 years ahead of you, but hopefully you're old enough to make a rational decision. And so when I come to a group like this, of any age though, I ask, would anyone, if you had the opportunity to travel fast and go to the nearest star, if we knew there was a planet around there, would you go there? And the thing is, there's always, at least, I can always ask this question because there's a lot of people who won't put their hand up, but there are always people who will want to go. And actually, I forgot to mention that in this case, that the 40 years is only a trip there. It's a one-way trip. So would you still go? I mean, the desire to explore is so huge and so amazing that one of our legacies of finding exoplanets is the thought that hundreds or 1,000 years from now, people going on this trip will actually look back at all of us here and they'll say, wow, those were the first people who went out and tried to find those Earth-like worlds. So that topic is a bit in of itself. It still has the giggle factor to it, but so did exoplanets in the past, so we'll see what happens. But can we go there? Not for now. So the people who ask that question, they always have the follow-up. If we can't go there, why look? And so we do have a real answer for that. And I like to call this actually the real search for alien life. And here I'm not talking about aliens that may have visited Earth. I'm not talking about searching for, little green people, although we all want to be able to hopefully meet intelligent life someday. That's not what I'm talking about. We're talking about the search for gases in an exoplanet atmosphere that might be attributed to life. Now, just for the people who might not know what a spectrum is, I wanted to introduce the concept. And I'm sure that all of you have seen a rainbow. If you could look at a rainbow closely, you would see that some parts of the rainbow are missing, actually. Not huge chunks, not like whole colors, but little lines. And those lines are missing because partly of absorption from Earth's atmosphere. The gases, I like to say, they take a bite out of the spectrum. And here's an image actually of our sun. And our sun also has an atmosphere, we call it the photosphere, where atoms are doing some absorption. And if you look here, all of these, there's like a fingerprint. Each atom and molecule absorbs with a different width and a different depth at a different wavelength. Can you see here? Some of the lines are quite wide, some are narrow, but actually people have worked for many decades to understand all of this. And here, just to summarize this part, spectra are required to identify a planet as Earth-like. And as an example, Earth and Venus are about the same size and mass, but one planet, that's Earth, has life, and the other is completely inhospitable to life. So actually, last night, for those of you who are here, was called squiggly line science. Squiggly line science. And what it means is what we would really do is not look at an image like this, but actually translate this into how deep are these lines. Does it really go to zero where it's dark? What are the edges like? See, some of the edges are a little blurry. Are they, sloped or short? And what we'd actually call a spectrum is this kind of cartoon sketch here, showing you a water vapor signature, what it would look like as a function of wavelength and absorption here. So it was called yesterday squiggly line science, but believe it or not, there's a lot that goes behind this, quantum mechanics, and it's the way molecules interact with light and computer codes to figure out what would be there. And what this cartoon diagram is showing you is, again, remember the transiting planet we were talking about? Well, as the transiting planet goes in front of the star, some starlight can shine through the atmosphere. And we have, with several exoplanets, picked up the spectrum of the molecules in the atmosphere. And we've identified things only on big hot planets, like water vapor. We've seen things like, some things are somewhat controversial, but we've seen like sodium gas and potassium gas and a bunch of other molecules. So that's what we hope to do. And here's a picture of the James Webb Space Telescope, because I'm here to partly tell you that the James Webb Space Telescope will follow up the planets that we find here by various methods from ground-based telescopes and space-based telescopes. We're going to look at the atmospheres. And that's what we hope to do, is have the pool of small planets or super-Earths transiting small stars. And then we're going to use the James Webb Space Telescope to look at their atmospheres and to look for signs of gases that may be produced by life. Now, for the people who are astronomy buffs in the audience here, do you know what the Hubble Deep Field is? The Hubble Deep Field is when Hubble looked for about 10 days and 10 nights at a small patch of the sky, looking for what could possibly be in a dark region where nothing appeared to exist, and Hubble found untold number of galaxies. Well, the study of exoplanet atmospheres with the future James Webb Space Telescope is actually equivalent to that. We'll have to take literally 100 hours per planet. That's for astronomers, that's a lot of space telescope time just to try to find this signal. And here's actually an image of Earth spectrum. Earth spectrum, you can see in blue there, I'm not going to go into detail on it, but each feature corresponds to a different molecule. Some features correspond to the same molecule. And if you could, if we had more time and we could analyze the spectrum and talk about how Earth spectrum formed, you'd know that it contains signs of life and signs of habitability. And so here on Earth, we have one really great example of what we call a biosignature gas, and that is oxygen. Oxygen is produced by plants and photosynthetic bacteria. Without oxygen, we wouldn't be able to exist. But without life on Earth, we would have virtually no oxygen. We'd only have the tiniest amount, barely detectable at all. And oxygen is such a highly reactive gas, it shouldn't be in the atmosphere at all. And actually, you know what? If there is an alien civilization orbiting a star not too far away, if they're the same technological capability as we are, and they have money to spend on space science like we do, and they funnel it all into a space telescope, they actually could see that we have oxygen. And they would actually wonder, why is there so much oxygen, many orders of magnitude more than should be there? And so I hope they're out there, they're looking back at us, but that's what they find, and that's what we aim to do. We aim to look at spectra, to look for signs of life. So if we can't go there, why look? The answer is we want to do remote sensing to search for gases in a planet atmosphere that might be attributed to life. Okay, now I just have a few more slides, but I wanted to tell you one more thing, okay, before you go, because that's not the end of the story. But I wanted to spend my talk telling you something that's happening soon, finding planets around a nearby star and the chance to find the sign of life. This whole time scale for this is about a decade by the time the space telescopes get launched and we have time to observe and get data and sort through it all. But transits are only the first part of a very long story. Transits are limited to planetary systems with a fortuitous alignment. They have to be going in front of their star as seen from the telescope, but in fact, the orientation could be anything. And so these planets are actually quite rare. So I'm going to finish off by telling you about a longer-term approach, and this one, I can't hide my enthusiasm for it. It's what I spend all my time on these days. But we call it the direct imaging approach. It's also underway, and this is showing you, if we try to look at a star, we just see all this glare. Remember the searchlight analogy? The firefly next to the searchlight? And so what we have to do is find out a way to block the starlight so we can see the planet directly. Here they miraculously appear. Got to block the starlight, and we actually want to do this. And you know what we want to do, actually? Is we want to build a screen, a very large screen, just like it showed in this cartoon, and put it in space and block out the starlight. It would just be like you turning around and looking at these bright lights here and blocking out the light. Only instead of your hand, it would be a big screen about tens of meters in diameter, and it would have to fly tens of thousands of kilometers away from the telescope. So here's an animation describing this concept. The telescope and starshade, we call it the starshade, could launch together. They would separate, and the petals would unfurl from a stowed position. A central hub, a truss, would expand, and the petals would unfold and snap into place. These petals have to be manufactured very precisely to hundreds of microns in width, and they have to deploy to essentially millimeters with respect to each other. The starshade would have to fly tens of thousands of kilometers away from the telescope, and it would block out the starlight to see the planets directly. I just for 1 second wanted to explain why it's such a special shape. And that is because if we have a circular screen and a star that's a point source, we actually won't see a point source. We'll actually see ripples. Light acts like a wave and actually can create ripples, light ripples. It would be dropping a pebble into a pond and you would see ripples, but those ripples in light, they're way brighter than the planet you're looking for. By making it a very special shape, essentially, those ripples are pushed out to the edges. And in that way, you actually use diffracted light to your advantage and can look it up. But there's a lot that goes behind this, and it wasn't really the main topic of my talk today. But I actually wanted you to know that we're working hard on this in the lab, and this is from Northrop Grumman and NASA JPL and Princeton. Here it's going to show you a test in the lab. This is like a full-scale starshade. Went the wrong way here. You can see, this is from August 2013, you can see the petals. These are the prototype petals made up of special flight-like, they're carbon fiber materials, unfurl from a stowed position. And this is a real time. They made 4 because it's all they could afford to make, but it's enough to test that the way they latch onto the central hub. The central hub, by the way, this particular one, it's left over from large radio deployables, so it has heritage of big things that have been launched into space before. Now it's showing you a time lapse of the truss expanding, just like in the animation, and the petals are going to unfurl and snap into place. I always get asked, why are there people in this time lapse? And the goal wasn't to show an automatic deployment, which has actually since been demonstrated, but to show that doing this 25 times in a row, the petals actually unfurl and they get placed in the same position relative to each other within the required tolerances. So the Starshade is an ongoing project. There's no launch date, there's no guaranteed funding for this yet, but it's something that actually, I'm chairing this big concept study that's going on now, and we're gonna wrap up our study in January. So to summarize my talk, I went through what is an exoplanet. It's a planet that orbits a star other than our sun. I showed you a few examples and showed you that there's this huge diversity in other planets out there in our nearby our own sun, in our own galaxy. When and how will we find another Earth? I told you about our short-term technique of finding transiting planets going around small stars. And I explained briefly how we will try to look at their atmospheres using a future telescope called the James Webb Space Telescope to look for gases that don't belong that might be attributed to life. I just want to summarize that I want to remind you that, people born today, to them, exoplanets have always existed. In fact, if you meet university students today who are in their 20s, to them, same thing. When they became aware of the world around them, it was a known fact that there are planets out there. And we actually want to take that to the next level. We would hope that we don't say hope, we plan that someday we'll be able to take our children and grandchildren, and I don't add the word great-grandchildren here because I'm serious about this search, our children and grandchildren, nieces and nephews, to a dark site, and to point to a sun-like star and say, that star has a planet like Earth. Thank you for your attention. And, I forgot to mention, one of the questions I always get asked is about UFOs and whether or not aliens have visited Earth. And I just answer, that's not what I work on. I don't actually believe they've ever visited Earth. But I'm really pleased now to pass on to Joe Nickel, who will actually, the title of his talk is UFO Mythologies.
Forward?
Yeah. Right.
This one.
Yes.
Thank you. Thank you for coming out. I'm really pleased to be in Montreal. Of course, when you get older, you're pleased to be anywhere. But it's particularly good to be in Montreal. I want to thank Joe Schwartz for his really heroic work in doing this and putting this together. And of course, Lauren Trottier for his vision and putting his efforts. Yes. Okay, we've just embarrassed him, but that's all right. This is very, very wonderful. I want to talk about UFO mythologies, but part of that is talking about Bigfoot, so I hope you'll bear with me because it's really part of the equation that I'm working on. As you may know, most people's talks are thinly disguised commercials for the books they've written, and this talk will be no exception. What do we mean by a myth? Well, when folklorists, I studied folklore as part of my doctoral work, folklorists don't use the word myth to mean just something that doesn't exist. They use it to mean something more like this. Myths are narratives that present paranormal topics as explanations or metaphors of cosmic or natural forces or the like, creation myths, for example, and that often involve super beings interacting with humans. Now, when I put that definition forward, I want us to think in this way, that when you and I tend to think of mythologies, don't we mostly think of those ancient Greeks and Romans? And what I'm wanting to suggest to you is that right now, you and I can see in our time two very vast mythologies that meet these criteria that are all around us, and we can watch them develop. The term myth doesn't mean they don't exist, but it certainly puts them into a perspective. And one of those, of course, is Bigfoot. Now, we tend to think of these questionable beings in our own terms. We tend to see them in our image. We invent them, if you will, in our image. For example, Bigfoot is sort of our stupid cousin from the past. E.T. is a futuristic version of us. Ghosts are us, maybe transparent. And vampires are us with an attitude. The laughter machine is working very well here. It's a really good auditorium. I like this. So Bigfoot. First, of course, another word from our sponsor. But here is Sasquatch. Here is the kind of work that I do is to go out not to not to debunk. I'm called that as if it were a dirty name. I'm called a debunker by really angry people who are basically saying, how dare me question their emotional belief. And I don't think that I'm a debunker in that sense. If debunker means someone who's solved a lot of things and shown that they were bunk, okay, I accept that. But if it means someone who's dismissive, a sort of armchair put-downer, or someone who wouldn't get out of his armchair to go check something, that I hope to convince you is not what I do. So I'm out doing field work. I'm a former detective, a Pinkerton detective. I'm a former magician. I was the magician at the Houdini Hall of Fame, and I've tried to put these together to become a sort of magic detective, title of another book. And it's a children's book, and maybe one of my best received books. But I'm going out trying to explain a mystery, confident that if I can explain it to you and you buy it, that's a reasonable explanation, then any needed debunking just takes care of itself. I don't have to have an attitude to debunk. I'm just going to try to find the answer and explain it. So I have done field work in the Pacific Northwest. Here I am in the area of Bluff Creek. We'll talk about Bluff Creek a time or two. I have been in the rainforests in the Blue Mountains of Australia looking for their fabulous creature known as the yowie. I've been to south of Beijing. I was a visiting scholar in Beijing for a time and was able to go to a place south of Beijing called Zhoukoudian, and that's the place where the famous Peking man fossils were found. And in China, they have a creature known as the Yeren, and some people believe the Yeren is a Peking-type man, an ancestor to man who's just stayed on. He didn't disappear. Now we talk about the question of evidence with Bigfoot. We've had legends of something called Sasquatch for a long time, but Sasquatch is not a name used by the native peoples, although a lot of people think it is. It was made up by a school teacher who kind of harmonized several similar sounding words into Sasquatch. But in 1958, at a road construction site near Bluff Creek, as I mentioned earlier, these foot tracks began to appear. We now know that that was an elaborate hoax using carved feet by a man named Ray Wallace. Mr. Wallace is now dead, but his family still has some of these cutouts, and we know for a fact that he did that. This 1958 date is the real origin of the modern study of these fabulous creatures, and they were thereafter known as Bigfoot. The press called these Bigfoot humorously, and it stuck. So you don't hear Sasquatch as much now. Here's a footprint from Bluff Creek. And this is a footprint left by this creature. I'm sure all of you have seen the famous 1967 Roger Patterson Bigfoot film. I would show it to you, but it is very copyrighted. And this creature is not, I think, not really Bigfoot, but Big Suit. Okay, well, let's try that again and see if we can get a little more laughter. Really known as Big Suit. Very good, very good. My old friend Steve Allen used to say, he whispered it once in my ear and said, timing is everything. So we now know that that famous picture of Sasquatch / Bigfoot was a hoax. Now, I know there are true believers who just believe that this is the Holy Grail film. This is absolute proof of such an animal. But I think they're ignoring a few things. One is that there's no fossil record for this Bigfoot. This particular image is often defended on the grounds that no hoaxer would have thought up making a female Bigfoot, that this just wouldn't have occurred to anyone. The pendulous breasts were just, no one would have thought of that. Well, let me tell you, a year before this, Roger Patterson published a book in which he had a drawing of just such a creature. And Roger Patterson is what we call a repeater. He's a guy who would go out and find Bigfoot tracks and go out and see Bigfoot. And he went out with a 16 millimeter camera, and he decided he was going to film Bigfoot, and Bigfoot showed up almost on cue. This will not surprise, I think, most of my audience. But I know the person who sold Bigsuit to Roger. And his name is Phil Morris. He's now has a huge costume factory. He's one of the biggest costumers in America. And Phil sold him a standard gorilla suit and some extra furry material to make, as we now know, what he used it for, the breasts and to reshape the head so it didn't look so gorilla-like. And I remember that we also know who was in the suit. His name was Bob Hieronymus. And there are people still living who remember Bob showing them this suit in the trunk of his mother's Buick. So we're really getting some real evidence at long last. Now, when Roger rode out to make this film, he went out with a guy named Bob Gimlin. And I've met Bob and talked to him, and I'm afraid that I have to tell you that Bob is going to go to his death keeping this secret. He's not going to tell on his friend Roger, I'm afraid. But it maybe the best statement that was ever made about this was made by John Napier of the Smithsonian. And he said of it, quote, "I can't see the zipper." And I think that expresses it all. This remarkable creature, known as the Minnesota Iceman, billed in carnivals as Sasquatch safely frozen in ice. And this created a sensation. There were a couple of scientists who thought it was maybe a preserved Neanderthal. They were taken. It looked very, very realistic. I was able to see this in a carnival sideshow, and I got really lucky because they had a problem with the ice box that it was in. The power had gone off, and it had begun to melt, but they were still selling tickets. And when I got in there, there was actually an exposed patch of it that was free of the ice, and I was able to reach over and touch it, and I'll use the word rubbery. So we now know, of course, it was made by a Disney model maker, and it was a wonderful piece of work, but no more than that. Now, I have labored to try to explain some of the monsters. We know that lake monsters often have a long neck, they have multiple humps, they swim in an undulating serpentine fashion across water, and they're 20, 30 or more feet long. And science says there can't be such a creature, but I've met many of these people, been in their homes. These people are sane, they're sober, they have absolutely seen something. So how do we settle this thing? Well, I happen to know that there is something that looks very much like that in nature. It's called Lutra canadensis, the northern river otter. And you're thinking, no, wait a minute, the otter is not that long. Right, but imagine 3 or 4 juveniles playing follow the leader and try to imagine how that could look like one serpentine creature. Or a mother and pups. And in fact, I have met real people who have actually seen that illusion, been fooled by it, one a wildlife expert, and then saw what it was. And they'll tell you this is the damnedest thing. Well, let's apply a little bit of that logic. I don't mean, of course, that all lake monsters are otters. Some are beavers. And there are other explanations. And thank you for laughing. That's a new joke I'm testing. So maybe a keeper there. But what about Bigfoot? What are people seeing? Because again, I'm not saying they're all hoaxes. There are a lot of hoaxes, hoax tracks, of course, hoaxed sightings, people making up stories. But some people have seen something. What is it in North America that looks so very much like Bigfoot? This is what's called a split image drawing. Look at that hairline, and the black bear and the brown bear. I think most of you know now, people know more about bears, but people seem to not to be aware that bears frequently stand on their hind legs, stand upright, and can walk some in this mode. And they look remarkably like, I would argue, like Bigfoot. And when you see some of these reports, people say, yes, I saw Bigfoot, and it was in a berry patch. It was very, very far away, and there were 2 smaller Bigfoots, and they were on all 4s. And then the obvious parent Bigfoot dropped to all 4s and ran into the woods. And you're thinking, what did you miss there? So again, I'm not saying that all Bigfoot reports are bears. People think I'm saying that. The Bigfooters are making fun of me. But some of these, for example, a report of one that was bluish color seen at night up in the Yukon Territory. And in that area of Alaska and Yukon, in that very small area, there is a type of black bear called a glacial bear that has a distinctive bluish coat and blue-gray face. And I think, again, probably saw a bear. And there are just lots of these cases. So Bigfoot has become now part of our mythology, and it's everywhere. Here you can see an action figure, you can see a Bigfoot rescue kit novelty. In the center is Bigfoot ale, and on the right, a kind of Bigfoot folk art or souvenir, sort of homemade. And you can find these now across America. And this is proof that this is a mythology with real staying power. Here is the link between this, and here is an extraterrestrial who looks very much, would you not agree, like Bigfoot. And there are reports of UFOs associated, UFOs seen where there were Bigfoot sightings, and just quite a lot of mixing now of these 2 endeavors. So we're seeing Bigfoot is representing our past and sort of the very symbol of the endangered species. I think Bigfoot is so endangered that it may not exist. What do you think? But we're now turning outward from this little planet, and we're looking at extraterrestrials, and we're developing this other robust mythology. Another word from our sponsor. I did not write this book. This was an international runaway bestseller, Chariots of the Gods. Most of you who are my age or even younger are well aware of when this book came out. It really just took the world by storm. And it was the idea by Eric von Däniken a kind of, shall I say, almost to me, I found it offensive in a way, almost racist to my mind, because of the way it suggested that ancient non-white people couldn't have built things like the pyramids or the stone statues on Easter Island or other great structures. And I think we know that they did. And I find it really kind of offensive the way he presents this, as if these sort of primitives or savages had to have extraterrestrial help. And that now is called ancient astronauts. And it's a whole genre of belief in ufology. Well, I want to show you, much of what I'm going to show you is my work. Kind of like if you had Bob Dylan come and sing, he'd probably sing his own songs instead of Frank Sinatra's. So I'm going to show you some of my work. I've done no work, listen to me carefully, no work on the pyramids. Not planning to do it in this lifetime. But the Nazca lines across 30 miles of no man's land, desert pampas in Nazca, Peru, this plateau area, are these ruler straight lines, these figural images of all sorts. This is the giant condor. And to put it into a little context, here are some of the other Nazca figures to scale. And just look at that condor in the center, because I'm going to show it to you again. That is 440 feet long, a football field and a half. It is so big that when I decided I was going to duplicate it and stuck a post on a landfill and measured off 440 feet and stuck another post, even though I thought I'd figured this all out and was pretty confident of what I was going to do, I gulped. This was a big, big bird. So these figures are so large, they really can't be seen well except from the air, from about 1,000 feet. So you can see why von Daniken would capitalize on something like this. He envisioned that spacecraft hovered over and beamed down instructions to awed savages so that they could make these. But of course the desert is soft, and any spacecraft that tried to land there would probably get stuck. But nevertheless, here are these Nazca figures, and here is me, much younger and thinner, done back in the 80s, using, I made it a rule not to use anything like, anything that measured an angle, no surveying equipment, nothing the Nazcas couldn't have reasonably had. So I used just some cross sticks and a pair of cross sticks for sighting and some knotted cord to measure by. And I made this giant condor. It may look like rugged ground. This land, you'll see in another picture, is mottled dark and light because it's the landfill, so there's sort of, some black coal and some white clay and stuff. But it's, trust me, as you'll see, it's flat as a pancake. Scientific American said my recreation was, quote, remarkable in its exactness to the original. In fact, I copied it so perfectly, I copied its mismatched wings. And here I am, oh, that thin fellow. There he is, standing in the giant claw, to give you some idea, and this is from a stepladder, so you can see a little bit of an area, but you can't really see the whole thing. But you can figure out what you're doing and be able to visualize it in parts and have a system, and you can mock up from about a 6'1" to a 440 feet. So this was successful, and decades went by, and then National Geographic called. And they said, we would like you, ancient geoglyph creator, to come out of retirement and make us one. And I said, oh, please don't make me do that. I'm getting old, and it's a lot of work. And I tried to beg off, but they finally, had the clincher. They said, yes, but you didn't film it. Oh, you got me there. So they were going to get a cherry picker, and they rented a ranch in California, and I finally agreed, particularly when I realized, of course, the spider's not nearly as big as the giant condor, and I made this. Ladies and gentlemen, I give you Spider-Man. And they were very happy. We got about halfway through, and I saw the cherry picker coming down, and I had it about half done, and the producer came running up, and she was just excited. She said, "It looks great. It's just looking so good." And she said, "We thought we would break for lunch, but wow, it's just looking great." She said, "Would you like to come up and see?" I said, "Are you kidding? That would be cheating." "Oh," she said, "right, the Nazcas didn't have cherry pickers too." I said, "Yes, exactly." She said, "I withdraw the offer." So we went to lunch. After lunch, I made the rest of the giant spider. Why did the Nazcas make these? Well, I call your attention to the fact that these figures are all, unlike Nazca pottery, are drawn with a single line. Once the pen is put down on the giant drawing board, it's drawn. It never lifts till it comes back to the beginning. Whereas on the pottery, you draw a head, you lift your brush, you draw a wing, you lift it, and so forth. What was that about? And you notice that the spider, for example, has these extraneous lines going off the foot. And the monkey has two extraneous lines going up to the base of the tail. And those have nothing to do with layout. They're not part of anatomy or anything. But I think I can tell you what they're for. And I don't claim to have discovered this. A friend of mine, Tony Avini, and I and others have been working on some of these projects for a long time. Tony's an archaeologist. But if you walk in one of those lines and just continue, you will traverse the entire figure and come out the other one. And the smart money now is that these are giant ritual walking paths. And I leave it to you if you can find a better hypothesis, but I'm reasonably confident that's what they were about, and that they were made by the Nazcas, not by spacemen. Well, let's talk about UFOs a little bit. I didn't want to talk heavily about it, but everybody's heard of the Roswell incident, and the Roswell Army Air Force, it says, captures flying saucer on ranch in Roswell region. Now, that has become sort of the holy grail of ufology. And the question is, the Roswell crash debris, what actually happened is that a guy named Mac Brazel came into town one day, and he said crashed on his property was this debris, and he described it as foiled paper, sticks, tape, and rubber. Does that sound like a extraterrestrial craft to you, or does it sound maybe like some kind of balloon array with maybe a box kite-like thingamajig? Well, photographs show that, in fact, this is a corner radar reflector. This is something to pick up radar, this foiled paper. Of course, the conspiracy theorists say it's a cover-up. But I can now tell you what this actually was. It was a secret United States government spy balloon array called Project Mogul. Now you will all have to be killed, but no, it's okay. And I've personally talked to Charlie Moore from Project Mogul, and he's verified that this was a lost Mogul item. Here we are recreating that at half size, and so you won't find me in the picture there because I'm taking the picture, but I made this was for Discovery Channel, and we made one of these, and then because you have to have good TV, we had a rifleman shoot it down. And of course, the believers were convinced that this was not what Mr. Brazel saw, and the skeptics were convinced that this is exactly what he saw, and that's the way it remains. But then you remember the famous alien autopsy, and you remember this character who we now know because someone confessed to having done it, that we know that this character was from, listen carefully, the distant planet Latex. Okay. One more UFO case. A friend of mine, Air Force Major James McGahey, Air Force Major retired, is a former special operations pilot. That means he can't tell you what he used to do if you're special ops. And he's also an astronomer, and he and I have been working together. I'm a writer, he's not. And there was a very famous case that was known as the incident at Exeter, the Exeter incident, in 1965. And went unsolved for a long time. It's an old cold case, and I brought it up and brought it to him. I had some guesses, and he, no, couldn't be that. The salient point was that the witness saw it go, these flashing red lights that went 1, 2, 3, 4, 5, 4, 3, 2, 1. Pretty distinctive configuration of something happening in the sky. And James recognized this like you'd recognize an old friend. And this was, in fact, a refueling plane that had that array so the plane would be signaled to come in for refueling. And we think that's the solution to that. What are other UFOs? Well, they're everything from weather and research balloons, they're planes and helicopters, meteors and bolides, hoaxes, of course, bright planets, sometimes seen under unusual atmospheric conditions, space reentry debris, the list goes on, satellites even, and so forth. Did I mention hoaxes? Let's turn a bit to alien abductions, because this has become really quite a deal in our time. And the alien abductions are often happen like this. Someone wakes up at night and is unable to move and feels he's been strapped down. And the thought occurs to him because he's been reading, say, one of Whitley Strieber's books or something else on the subject, that he's aboard a spacecraft. And then he hallucinates and sees an alien being. This is a type of dream called a waking dream, in which you wake not from sleep to being fully awake, but into a state in between. It's called hypnagogia. And in that state, you see ghosts or aliens or vampires, whatever is sort of on your psychological mind. And this is responsible for many of these reports of alien abductions. Others are due to hypnosis, hypnotic regression, and people, quote unquote, remember when they were abducted. Let me just give you my definition of hypnosis: the yellow brick road to fantasy land. And many of the people I've done a study of people who were abducted by aliens. I did a study of 13 of these people that were in Dr. Mack's book on abduction, and marked them for fantasy-prone tendencies. One scored 4 out of 7 traits, one 5 out of 7 traits. The rest had 7 out of 7 traits indicating and suggesting fantasy proneness. So these are different type of person, and it has to do with that rather than with anyone ever actually having been abducted. Crop circles, the movie Signs. Here I am, of course, doing field research. Thank you. Of course, the definition of a scholar is a man out standing in his field. I studied crop circles up close and personal in England, and one of the things is that you have to look at the phenomenon and notice how the phenomenon is evolving. One is its geographic distribution, that it's found mostly in southern England. Then you notice that it's increasing in number. Each year there would be more crop circles made in relation to media coverage. And then they began to increase in complexity. There was a sort of one-upmanship each time. And then the fourth characteristic that we noted was that there was what was called the shyness effect, Now, this is my personal favorite. This has to be genuine if any of them are. Obviously, the aliens are wanting to communicate something to us. I'm not sure what. But in other words, the shyness effect is that these are in remote fields at night when the mysterious effect won't be seen making a crop circle. In other words, these are just a form of like graffiti. People go out and make them for sport. This one I know is fake because, well, I helped make it, and we made it in the field next to the one used for the movie Signs. We couldn't get that field, but we got a field of oats, and we had a wonderful farmer, a one-armed guy who was a real character, and he was happy to let us go make one. Now, just a few more slides. I'm probably running close, right? Few more. Alien timeline. This is my comparison of how the alien image has evolved over time. Notice that we start out and we have little green men and we have Venusian creatures and the Flatwoods monster and hairy dwarfs, and they're just all over the place. Now, these are not fictional. These are the ones people claim to have experienced. And then, eventually, in 1961, you get the Betty and Barney Hill case. It's a little hard, I'm a little off the side here, but this one right here, notice this one is the little big-eyed, big-headed humanoid. This is the one that's the futuristic version of us. Our mythology is now developing where it's beginning to put us in just as Bigfoot as their beastly cousin from the past. And then eventually you see that one coming back and back and back until it becomes standard, so much so that this is some of my collection of about 100 aliens, another one from the distant planet Latex. And these are all, you see, this particular type, so it's becoming standardized. And remember that waking dream picture I showed you, it was of that type. Remember the Roswell autopsy one, again. So you can now sort of date when the aliens were evolving. So let me sum up what I've been saying. There's very little credible evidence that Bigfoot or extraterrestrials are on or are visiting the planet Earth ever, and I don't think they will be in the future. We're on this fragile little pale blue dot, as Carl Sagan called it. Our world is shrinking with it. Our wilderness is shrinking, and our species are threatened. Maybe we are too. Bigfoot is the symbol of the endangered species, and now with that mythology, we're looking out from the planet, out into the universe, and we're imagining that we're going to see life somewhere out there, and it's going to be somewhat like we imagine ourselves in the future. Vestigial bodies. Hey, a lot of us living virtual lives now. Maybe our legs will waste away, but these vestigial bodies, big brain case, big smart creatures, and this is our image for the future. So you and I are witnessing right now in our lifetime these two powerful mythologies, and they are as real as they can be to some people, almost like a religion, almost cult-like. And we do well to understand this and to talk about it respectfully to people when we can, but this is the nature of our work ahead. Thank you very much.
I must say that one of those crop circles looked very much like Professor Sager's unfolding screen. Maybe a coincidence, who knows? Okay, well, thanks very much to both of our speakers. A lot of interesting ideas brought up there. And we will have questions. Again, I would like to remind you that we are looking for questions, not speeches. So please approach the mics and we will answer the questions. But tradition has it that the first question on the second night of these symposiums should go to Lauren Trottier. So, Lauren, I'm sure that you have at least one question.
Keeping in mind that if it's a difficult question, I may revise and extend my remarks.
Well, now, hadn't really thought about this, but Professor Sager, I guess, you mentioned that oxygen, if we found a signature for oxygen on an exoplanet, that would be a pretty strong indication for life, and certainly in the case of the Earth, as you said, oxygen is made by life. But are there non-biological processes that could produce oxygen? And if so, what else could we look for that might indicate for life?
Yes, well, every time someone can come up with what we call a robust biosignature gas, the next person can come up with a reason why it's not so robust. So there's a sort of back and forth constantly. And one way oxygen could be produced that would not be by life is, imagine if we have a time when we think this happened to our planet Venus, where the planet warmed and the water evaporated, the ocean started evaporating, and they filled the atmosphere. And ultraviolet radiation split apart the water vapor molecules. Hydrogen escaped to space, and oxygen started building up. During that runaway ocean phase, we believe you would see oxygen. The good news is you'd also see heavy amounts of water vapor. And so in hopes that you could look at everything and put the whole picture together and say whether or not it was likely created by life or likely not. So I'm glad you asked that question, because there's a deeper answer. And that is when, I hope that I can be back here in 10 years and 20 years and actually say, wow, look here, we have a bunch of planets. But in any one, I'll never say that one, we're sure there's life. I'll say, here, look, we see this, we see oxygen, we don't see too much water vapor, we've thought about all the possibilities. I'll say 99%. We might have another planet where I'll say, well, we're only 50-50. And so in that way, we really need a huge number of planets to be sure that there is life beyond Earth, but any given one. Now, just to quickly address what other molecules may be produced by life, it turns out that life on Earth literally almost produces all small molecules one can think of. There's so many. All the molecules in our atmosphere, nitrogen, carbon dioxide, N2O, we could pick H2S, there's huge numbers of them that are produced by life, but they're also produced by volcanoes, or they're already occurring. So sorting through which ones could be produced by life for sure, which ones are also produced in other ways. It's sort of a very deeply ongoing field right now. So it's a good question, but there's no conclusive answer yet.
Thank you. The gentleman at the back.
Hi, excellent speeches by both speakers. I enjoyed them both immensely. I have a question for Professor Seeger. We learned yesterday a recently discovered and very promising avenue for life are places like Enceladus, Titan, Europa, places very much outside the traditional Goldilocks. We know that they generate heat by gravitational forces caused by their parent planet. Any Star Wars fans know in the original movie, the Rebel base was on the moon of Yavin, this lush jungle planet that was a moon of a gas giant. And so, given that kind of progress, how do these type of objects change the variables that exoplanet researchers look at? How are you going to tackle the challenge of finding such planets, since they're very much outside of our traditional understanding of how life can be?
Right, so just to re-summarize the question, there are so many, I talked about the habitable zone and planets with atmospheres and surfaces with water, but there are also moons. Life lives beneath the surface of Earth at the bottom of the ocean. There's moons like Enceladus where we think have water and other ingredients for life. And the answer is in exoplanets, our job is so impossibly hard to find life where we can that we usually don't even talk about life that exists in ways we'll never see. Moons, for example, we have not yet found an extrasolar planet with a moon. And if we did, it would be nearly impossible to look at it. So right now it's off our radar because it's too challenging. We can't see life unless it produces a signal that fills the atmosphere. So we're aware of it, but we just drop it for now.
In the front.
Hi, I'm sorry if this was mentioned yesterday or addressed yesterday, but one of the compelling questions seems to me that, and I love reading this subject, Paul Davies just wrote a book on it, and that is, why haven't we been visited yet? And there are all sorts of competing theories saying that they are here, but they're so smart that they're concealed, or that why bother visiting us? There's no value added. But one of my favorite new theories is that as soon as a civilization achieves virtual reality, like the holodeck on Star Trek, they just stop then, because now they have perfect life, and why progress after that? So I was just wondering, either of you, if you have your favorite theory about why we haven't been visited.
Well, I think it's just great distances, and I don't know if there's life out there. I don't think anyone knows that, but of course we all have our opinions, and there's a spectrum of opinions. I remember, though, just on a humorous note, when the famous Phoenix Lights incident happened, and I got a call from a reporter, and they want to tell you something that's allegedly happened, and then they want me to explain it within 30 seconds. And I just don't work like that. But it was sort of like, well, what was this? And I said, I have no idea. And he sort of like, see? And I'm thinking, you don't understand that you just have negative evidence. You don't actually have anything. It's just unidentified, and you're using an argument from ignorance. That is, you're saying, we don't know what it was, therefore we know what it was. And this is just a great logical fallacy. And this, I just share this with you, this is the secret to most of the paranormal, is that it's all negative evidence. There's no corpse of Bigfoot or anything, but we have, of course, we don't know, and then, it's great mystery, and we use words like unsolved and unknown and unidentified, and the implication is that we have something, but we don't have something. But anyway, I said to this guy, I said, well, I think eventually we'll know what this was, and we do know what the Phoenix Lights was. It was a squadron of planes, and they dropped some parachuted flares as a military exercise, and we know that for sure. But I didn't know it at the time, and I just said to him, I said, whatever it was, I think the least likely possibility that it's extraterrestrial life. And he just went after me that quickly. Why do you say that? And I said, well, I just can't understand why the extraterrestrials are coming on what would seem to be some sort of clandestine mission and hovering over Phoenix with their bright lights on. Anyway.
Well, I'll just say briefly that I don't really speculate on that. I'm going to wait until we have signs of life on a number of planets. And if we actually find that life is out there, at least in some kind of microbial form, or we don't know what it is, then we can start speculating.
In the back.
Good question.
Are we alone searching for life out there? This is a very user-friendly way of presenting and promoting very expensive exploration. To what extent is the search being driven by the military-industrial complex, including mining companies, who in reality are more interested in exploring Mars and other planets for their strategic positions and for rare and valuable materials? And would this billions of dollars not be better spent in our precious planet combating malaria, the greatest killer of all time, cancer, and Ebola, which my 16-year-old niece is certain are ideal alien forms of biological warfare? So have you...
Sure, well, we get asked this all the time. Why are we spending money on this? And I think everyone may or may not have a different answer for it. We actually had a roundtable discussion about this, which I believe is taped, so you can hear more than one person's opinion on it. One of the concepts we like to try to promote and explain to people is the sort of creative process of pure science and what it leads to. Things that are a part of our everyday life, medical imaging, the laser, which everything now is scanned. It's involved in surgery. Many things come out of pure science. When we try to do something just for the sake of doing it, we end up in pure science. That's one reason. Another reason, so we need to make huge progress, we need to just do pure science, even if it seems like the so-called random walk. Another thing that, my favorite reason actually for defending exoplanet science and the search for life is just the inspiration it gives to the next generation, who will go on and maybe the ones who find the cure for cancer or solving the problems of diseases that appear and spread we're getting all these people interested in science. You know, it's a problem in North America especially to draw people into these fields instead of doing other things. So we can give you millions of reasons. We can say, you know, it's just a jobs program, really. We're taking taxpayer dollar and converting it to something else, and there's the trickle-down effect, so many, many, many other jobs are supported. And you know, as a world, as a species of humanity, should we be doing really hard things, building big, complicated space telescopes just so? Should we be creating, you know, great works of art? So we have many reasons for doing it, but I think we won't be stopped. I mean, people are born explorers, and space is out there to explore.
Thank you.
Okay, we'll take a few more. Everyone who's now standing at the mic, and that's going to be it. Okay, gentleman in the back.
Hello. First of all, thank you for the wonderful speakers. I would like to know, in this age of reason and scientific knowledge and all what we've been learning about our universe, what is your approach, you as educators, about the claims of people saying that we live in a universe less than 10,000 years old and no evidence to back those claims? Do you think it's a threat to our future and to our scientific discoveries, or just a little stone in our shoes, like we can keep walking, but it's a little annoying?
Okay, well, can you just repeat the question more concisely? I think we're saying, how do we approach people who have their own theory of cultures that say our universe is 10,000 years old?
Exactly.
Is that what it is? Well, it's really quite difficult to convince people who just want to believe in sort of a history of stories rather than follow the sort of scientific process of theories that can be, you know, use evidence to be restructured. So it's a challenge to get people to understand the scientific process. I don't think I have a good answer for you in particular.
But do you think it's a threat to our future? Like,
is it a threat to our future? Yeah. I think it is, actually, because it's, you know, hard to convince people of other problems that are going on in the world if they're sort of unable to use logic and think through the scientific process.
Thank you.
I guess this is more a general comment in response to a comment that was just made. So I can say as much as 50 or 60 years ago, there was research being done on viruses that infected chickens and caused cancer. And 50 or 60 years ago, someone would look at us and say, well, why do we care? But the thing is, the information that we learned from that, we've been able to adapt, and it's really revolutionized the way we're treating disease today. So it's the information that we learn is valuable. You may not be able to apply it now, but it has a purpose. That's all I want to say.
Thank you.
Yes, thank you. That's exactly correct.
At the back.
Yes, hello, and also just want to say wonderful talks, very wonderful. I have a two-pronged question, one specifically for Professor Sager and one for Mr. Nichols. For Professor Sager, I just had curiosity, are we any closer to solving the Fermi paradox than when it was proposed decades ago?
We are not, and we had a version of that question a little earlier. We do not know. That's why are we alone? Why haven't people contacted us if they're out there? Why haven't they colonized the galaxy? Nope.
All right then. And for you, Mr. Nichols, do you find there's a thin line between those who will very strongly persist in believing what is demonstrably untrue, and that sort of thing being a danger to, say, the scientific method, to progress, or anything of the sort? Like, can it be culturally poisonous? That kind of belief, that kind of line of thought, believing in something as small as Bigfoot or ufology.
Well, I'm obviously,
especially since that sort of thing is often an exploitable industry by those who say prey on the superstitious and etc.
Well, ignorance and superstition threaten us every day, and science is a candle in the dark, and we hope that we're able to convince people that through education that they can use critical thinking skills and do better. We're not going to end belief in UFOs and ghosts and all these things. It's not going to happen ever. But the way I see it is, It's really like saying that, and I've had people announce, oh, we finally figured out what all the UFOs are really, there's nothing to it, so let's move on. And meanwhile, a new generation has come up, and it's all new to them, and they're fascinated with some of these possibilities. But in fact, we're like firefighters. We put out some forest fires, we save some property, and we don't end forest fires, but we make a difference. And we just have to hope that people like us who care and use critical skills and use the scientific method, we get attention out of all proportion to our number. We're very effective, though we're often seem like a minority. But we do have an effect, and I'm hopeful that we'll save the planet.
That was a beautiful analogy, sir.
Thank you.
Thank you for your time.
Well, I think you appreciate that to put on an event like this that we've had over the last 2 days does not happen overnight, and there's a lot of effort that goes into it. So I'd like to thank some people. Certainly the AV crew is wonderful, and they solve problems all the time, and they produce a fantastic program. Everything that was here over the last 2 nights is recorded. It will be available to be seen on the web, including the roundtable session that we had with all of our 4 speakers and some McGill faculty and reporters, where we discussed a lot of questions in detail, some of which were alluded to here, but much more elaborate discussions. That will also be available on the web. My colleagues in the Office for Science and Society, of course, contribute greatly to this. But the organization of this is just a monumental task, as you can appreciate, everything from rental of equipment to making sure that there are hotel rooms and transportation, all of this could not be done without the help of Emily Shore, who has now done this for 5 years. And for next year, we'd appreciate if anyone has any ideas what you think you would like to see and hear in terms of scientific topics. I'd certainly like to hear that, and then we will discuss it. And we usually choose this sometime, within the next 3 or 4 months. So if you have any ideas, certainly we'd be happy to hear them. And of course, we get tremendous collaboration from McGill, from our administration, from Dean Martin Grant, from Provost Massey, who we heard from yesterday. And many of our colleagues attend, so we appreciate their support. And I think we've had a good number of our students here this evening as well, whose eyes have been opened to worlds that are out there for them to explore. That's why they are here at McGill, and their eyes open, ready to take in all this information. And of course, finally, thank you all for coming. And one thing that we have learned here in these 2 days is that as far as the search goes for scientific information and interest, we are not alone. And that to us in the scientific realm is very satisfying, that there are so many of you who are interested in the kind of discussions that we've had here. And hopefully we will see many of you next year on a subject yet to be determined. Thanks very much.